guys, in this video, we will be learning about the derivation of the Doppler effect equation. That's always given in your book, but it sometimes makes sense, sometimes doesn't make sense. So let's make sense out of it. All right, so let's understand by an example that we have a source, and that source for now is stationary. All right, the source is stationary and it's emitting sound waves of constant frequency and constant wavelength. And we know that when a source emits sound, the speed at which the sound travels in air is exactly 340 meter per second, or 330 meter per second. It changes, it depends, honestly. Now, the sound wave emitted earlier and the sound wave emitted later on has a substantial distance between them, and we call them the wavefronts. Each of these circles here represents a wavefront of the sound wave. Now, the distance between one wavefront to the other is said to be the wavelength of the sound wave. We can represent the wavelength of the sound wave to be lambda s. It's the wavelength, it's constant wavelength of the sound wave or of the source. All right, now let's provide here two observers. An observer X and another observer Y. All right. Now, since the observer here have stationary velocity, let's say, they're not moving at all from their own position. They're standing right next to the source. Honestly, some distance apart from the source, and they are same, and they are not moving away, neither towards, they're just stationary there. And the source itself is not moving either. In this case, the frequency of the source and the frequency of the source sound and the frequency of the observer is going to be the same in this case. But however, if the scenario suggests that the source is going to move towards observer X, if that happens, let's see what goes on. Now, at the same source, emitting the same amount of wavelength and the same type of same frequency sound, moves towards the observer X, what happens is, right here, the observer's observed wavelength somehow changes. Now, the observed wavelength is always the shortest changing wavelength observed by an observer closest to the source. Now, that's going to be this position. This is your new observed wavelength. And the wavelength's old position minus the wavelength's new position due to the motion of the source can be represented by the letter del x at this point. We can therefore illustrate these three variables right here, lambda naught, lambda s, del x, into one single equation. And that's going to be lambda s is exactly equal to lambda naught plus del x. And if you substitute or subject lambda naught right here, let's subject lambda naught right here, it's going to be lambda s minus del x. All right, let's recall what these variables really are. Lambda naught here represents the wavelength of the source that is being observed by an observer. In this case, that observer is X. Lambda S, however, is constant because the siren sound wavelength is not changing, and that's the constant wavelength. And del X is the same constant wavelength's new position minus the old position, or vice versa, depending on the velocity of the source. All right, now let's use the equation V is equal to F into lambda, equate this. You guys already know that lambda naught is the wavelength the observer X is experiencing due to the motion. Now, As an observer, you're going to hear a sound. That's going to be due to the speed of the sound. So this depends on v, which means speed of the sound, that is 340 meter per second or 330 meter per second over f naught. Because the observer is going to hear a different frequency, not the frequency of the sound because of the motion. So this is f naught. Equal to lambda s, however, represents the wavelength of the sound wave. So that depends on the speed of the sound and the frequency of the sound, which is also constant. And in this case, del x represents the source's or sound wave's new position wavelength minus the old position wavelength. So this depends on the relative motion or the velocity of the source. So this it can be due to Vs by Fs. All right, now let's equate this out. So it's going to be V divided by F naught is equal to V minus Vs over Fs. If you subtract this properly, this is going to be F naught is equal to Fs into V by V minus Vs. So V is 330 meter per second and Vs represents the velocity of the source. Here's the derivation for an observer's frequency due to the source moving towards it. All right, now let's look at another scenario for observer Y at this point. Now, this pink position here and this pink position right here are two wavefronts. Now, we know that this is not going to change, and that is lambda s. That is the wavelength of the source itself. Now, as I said earlier, lambda naught depends on the change in wavelength observed by an observer from the closest position. So therefore, the change in wavelength of the old one and the new one right here is going to be lambda naught. And this position right here, which is going to be del x, which represents the wavelength of the previous position minus the wavelength of the same source in a new position. So using these three variables right here, we can equate a new equation, which is going to be lambda naught is equal to lambda s plus del x. Lambda naught again depends on the motion of the sound itself over f naught. And then lambda s also depends on the motion of the sound itself divided by fs plus this, however, depends on the motion of the source. So it's going to be Vs over Fs. Let's equate this out. So it's going to be V over F naught, V plus Vs over Fs. If you cross multiply this entire thing, it's going to be Fs into V is equal to V plus Vs multiplied by F naught. Let's make F naught the subject right here. It's going to be Fs into V over V plus Vs. And these are the two equations here when an object is, when the source of sound is moving away from you. And this equation right here is for the source of sound that is moving towards you. The reason behind we used to give negative sign in the denominator when it's moving towards an observer, and the reason why we used to give positive sign, the sign to be positive when it was moving away from the observer is due to this derivation. I hope this was helpful.
If you guys found this video interactive and informative, please do like my videos and subscribe my channel. Until then, keep learning and keep exploring.